Hello. In this video, we're going to review for the final in 204. So notice that this exact document will be stored is stored in the final exam template. In the final exam week, you won't have access to the actual final exam until the time comes. But this file is a good place to start reviewing. So let's talk about algorithmic complexity. Given a code segment, you need to identify what its big O complexity is and identify the critical sections. Now, what is a critical section? A critical section is the part of the algorithm that is constant time and gets repeated n times. Every time n runs, every time the algorithm, the loop runs, normally a loop, this critical section gets repeated once at constant time. So n is the total number of elements of the algorithm that might increase without bounds. All right, the second item is JUnit, unit testing. Understand the three basic annotations: at before, at test, and at after. And the basic idea is at before runs before each test segment and test method, and at after runs after each test method. So the purpose for them running before and after test methods is so that there are no side effects from the test method. You can't write one test method that has side effects on another test method. Okay, hashing. Given portions of it, and this involves three things: the hash code, well, two things, the equals method and the hash code method. Write an equals method. If you have some kind of key, some kind of uniquely identifying element of the object, that's the best thing to use. So you could write, let's say a person has a social security number, a student has an M number, a car, a vehicle has a VIN, whatever these are, these key identifying elements. It's better to do that than to list up the first and last name, because first and last names might not be unique. So part B, what is a valid hash code? Any hash code that returns an integer is valid. Now, it needs to follow the hash code contract. That's a more difficult thing. But basically, the hash code contract says that anything that returns true from the equals method has to hash to the same element. So let's say 1, a hash code that returns 1. It's valid. It's the same for every object, but it's still valid. And it does follow the hash code contract, because anything that returns true from equals will also return the same hash code. So now a real world hash code involves more than just returning some integer. And one thing to remember is if your object has a string key to it, a key that is a string, in other words, a unique identifier that is a string, then string already has a hash code method. And it's easy enough to say this string dot hash code returns the value that you're interested in. So there is a very specific hash code method for strings. it may not be what's actually in Java, but it's pretty close. Your job is basically algebra to determine what that hash code method will return given a set of characters. And typically this hash code method takes the ASCII value of a character and concatenates it on and does algebra on it to the other characters in the string. Okay, graphs. Now we had some problems on the midterm 2 with the with graphs not being represented correctly in various browsers. So we tried a separate approach, and in this approach, you need to recognize that you need to go into the example final that's posted under the final template, under the final holder, and figure out how we're going to represent trees and graphs and so forth in the final exam, because there were some problems with how trees and graphs got represented. So given an adjacency matrix, so you'll get an adjacency matrix, you know what that is. Draw the graph that it represents, or show it. Now, in our discussion, we're gonna list a graph according with the V, the vertices, and the E, the edges. So the vertices are just one list of letters, either comma separated or not. The edges are more complicated because they go from one vertex to another. The best way to represent vertices or edges is showing one vertex and the other vertex. And for this exam, I would ask you to represent them in capital letters. And in the exam question, it says list them in alphabetic order. So A to X, not X to A, for example. So an adjacency matrix says the list of vertices down the rows and the list of vertices across the columns, and there's a 1 if the matrix has if the graph has an edge, and there's a 0 if it does not. For an adjacency list, the vertices are down the column like part B of the lab, and the values, the edges are listed out in the list. So notice A, you get an adjacency matrix, you draw the graph or show the graph with vertices and edges. Part C is just the opposite. Given a graph, and it's easier to show a graph, show the adjacency matrix. And D is the opposite of B. Given a graph, show the adjacency list. So understand how to do those 4 things. Given a graph, show the minimum spanning tree. Now the minimum spanning tree is shown by listing the edges or the weights. And frankly, that's the way the adjacency matrix is, or the adjacency matrix edges are too. So now there are 3 algorithms that you need to understand. You don't need to understand the code, but you need to understand the operation of it, the conceptual operation of it. So Prim's algorithm to find a minimum spanning tree. Kruskal's algorithm to find a minimum spanning tree. And then Dijkstra's algorithm. Especially Dijkstra's, you don't need to understand the code. You don't need to regurgitate the code, but you do need to understand what comes next, how the next vertex is displayed and so forth. You also, in part I, you also need to show in a directed non-acyclical graph, you need to show the nodes in topological order. Okay, trees. You need to be able to insert a list of integers into a binary search tree. Binary search tree. In other words, so there's a very specific rules about inserting integers into a binary search tree. So now, given a binary tree, show the array-based representation. That's a key to the 2i plus 1, 2i plus 2 rule. Now, that's not how you insert integers into a binary search tree. And the example final exam study slides will lead you to how we're going to represent a tree now. What is the root? What are the first, what is the left and right subtree root, and so forth. So given an array of integers, translated into, so the B and C are basically opposites of each other. Given a binary tree in a tree form, show the array-based representation. Given an array, show the binary tree it represents. And then do the in-order, post-order, and pre-order traversal. So now, part C. There are three kinds of copies. There's so understand shallow and deep. Shallow copy basically means that there are perhaps some shared objects. A deep copy means there are absolutely no shared objects. They're totally distinct. And then the third kind is not really a copy at all. It's just A equals B. You're setting the two variables equal to the same value of the object. Okay, for recursive algorithms, what is a recursive algorithm? It is an algorithm that references itself. It calls itself. A method that calls itself is a recursive method. So you need to be able to write one, a fairly straightforward one, but write one anyway. Remember that you have to call the method itself within the method. That's the definition of a recursive algorithm. And given a recursive algorithm, you need to identify the base case, the reduced problem, the general problem. Oftentimes the reduced problem and the general problem are combined into one, so that would be called the recursive algorithm. So be sure that you can identify the base case or perhaps plural base cases. Okay, threads. You're going to be asked to rewrite a class. That could be a little difficult, but you need to rewrite it to put various aspects in threads. So you need to be able to create a thread. You need to be able to start a thread. Figure out that it implements thread, implements runnable, and then the runnable interface requires you to implement the run method. All right, so you've done number 9 several times. Oh, wait, let me go back to number 8B. If you share a resource, you need to put a lock on it. Okay, number 9. You've done this many times. The one thing that people often forget is that in order to understand what parameter is represented by the capital letter inside the angle brackets, you need to put that in the class header, in the method header, the class header. So you have many times replaced car, let's say, or person, or something like that, with a single capital letter. Okay, heaps. So we're not going to ask you to delete a node from a heap or add a node to a heap. But what we are going to ask you to do is a little more complicated, and that's to do exactly what the heap lab had you do, which is first step, given an array-based binary tree, turn it into a minimum heap or a max heap, one or the other, and follow the steps. The example test, I believe, has an example of that. In the lab, a lot of people simplified it. Don't simplify it. And then, given the second step is to sort the elements, understand the algorithms for doing both of those things, turning the tree into a minimum heap or maximum heap, and that involves the rightmost highest level parent to start with, and then you iterate through the parents. And then the sorting, once it's a min heap or a max heap, the sorting involves taking the top element, which is by definition the max in a max heap, and replacing it at the bottom and leaving it then for the rest of the element. Okay, so that is the exam review for the final, and I would suggest that you download this review sheet and study it in preparation for the final.